3F is allegedly about the normal distribution, and that is true. There is a lot of material in here about that, but also there are a couple of other things that I stuck into the heading up here. The idea of skewness, well, having a symmetric distribution versus a skewed one, and the normal distribution is symmetric, so then it makes sense to consider the alternative, like what would be something that's not symmetric, and that's where you get skewed shapes. And then the idea of relative standing, which you can apply to a normal distribution, but you can really apply that to any distribution. Or if you're going to compare values from two different distributions. So we'll get to all of that stuff in here. But first, the normal distribution, which is also called the Gaussian distribution sometimes, although usually when it's called the Gaussian distribution, that's mostly in physics, actually. And I think there's a good argument for saying that that's actually a better name since normal is kind of a subjective term, but the convention is to call it the normal distribution. And it's a bell curve, right? That's the part that I think everybody's pretty familiar with to start off with. And it's a perfectly symmetric shape, right? The left and right sides are going to be mirror images of each other. And it's characterized by two measures, like it says over here, the mean and standard deviation, because if it's going to be this bell shape, the mean is right in the middle. So if I turn the pen on right here, and you can kind of see the grid lines in the back, there's one that goes right up to that peak, and right there is where you would have the mean. The standard deviation is a measure of how spread out it is. So basically what happens is if you have a standard deviation that's really small, then what you're going to end up with is a bell curve that's tall and thin, because the area under the curve always has to be 1. So that's another property, really, although it's not specific to a normal distribution. It's true for any probability distribution, though, that the area under the curve has to be 1. So if you have a small standard deviation, you'd get, that's not very straight across, you'd get something that's sort of tall and thin. So let me see if I can draw one in here. All right, so tall and thin bell curve, maybe something like this. And if you have a big standard deviation, maybe you get one that's kind of short, but then really spread out, like the tail. It takes a while for the tails to get down to the axis. So something like that. And then this would go way out on both sides. So I guess this would be large standard deviation, and this would be small standard deviation. So the area under the curve's always got to be 1, and that's why the one on the right is shorter. Because then with a larger standard deviation, it's more spread out, so the tails are going to be thicker. So to counteract that, but to keep the area being 1, it can't be as tall. So that's why the peak is so short in the one on the right. And that's generally how this goes. And the notation, which I left a box for that, even though this part really isn't that exciting, it usually looks like this, where you have n for normal, and then you specify the values of mu and sigma. So like a normal distribution with a mean of 10 and a standard deviation of 3, you'd have one that look like that, right? If you were going to write it in shorthand. Or a mean of 0 with a standard deviation of 18, you'd write like that, right? So that's all that is. But you do see that notation a lot. And the other thing is that since the normal distribution is perfectly symmetric, all the measures of center are the same. So the mean, median, and mode, they're all the same value. The mid-range, that concept doesn't really factor in here, because with this bell shape, even though it looks like it touches the axis, really it just gets closer and closer and closer and never actually touches. So there is no real minimum or maximum value. So you sort of couldn't compute a mid-range here. But the idea of the mean and median being the same, that actually comes into play every once in a while. Because since the median's the 50th percentile, and sometimes you need to know that right off the bat, but if you know it's a normal distribution, which would have to be specified by the mean and standard deviation, you could go, oh, the mean and the median have to be the same, but we had to be told what the mean was, so therefore it's this number. All right, next thing. If you're looking at a couple of graphs, and I guess this really factors in if I scroll up for a second to this sort of chicken scratch normal distribution drawing that I made up here. So like when the mean would be larger or when the standard deviation would be larger if you have a couple of graphs. And I'm sort of proud of myself because I programmed these graphs. It took a little bit for me to get what I wanted. So it's not like I just wrote it up in 5 minutes. It was more like I wrote it up in like 40 minutes, but it's there. All right, so what we're going to do is for each of these, so there's one here, and then if I scroll down, there's one on the next page too. We're going to figure out what's the relationship between the two means and what's the relationship between the two standard deviations. So I put a little key up here in the corner of the picture. So the red one is distribution 1 and the blue one's distribution 2. So the mean is where they're centered. And if we look at both of these in this picture, it looks like they're both centered at 10, right? Like the top of the hump is where they're centered since it's a perfectly symmetric shape. So it looks like they're both centered at 10. So it looks like for the true statements, we're going to have one about the mean and then one about the standard deviation. So the one about the mean, it looks like they're the same. So that would be C. And then the other one about the standard deviation, well, those are clearly different. If they were the same, if the means were the same and the standard deviations were the same, the curves would be right on top of each other. They'd be exactly the same curve. But here it looks like, so the red one's kind of squat, like it's shorter in the middle, but the tails are thicker. And then the blue one is really tall and scrawny, right? The peak is way, way up there, but then the tails are really short. They don't stretch out very far to the left and right. So the red one has a bigger standard deviation because the tails stretch out farther. So that would be D, right? Standard deviation of distribution 1 is bigger or greater since the red one is 1 and then the blue one is 2. So it looks like the standard deviation is bigger for 1, right? Because the tails are thicker. That's the thing that you look at. So for that one, it's thicker tails and I guess and shorter peak. For distribution 1, which is the red. Right, so it looks like that's what we got going on there. Okay, what about the next one? So the next one, okay, here it looks like there's nothing that's going to match up because it looks like the mean of the red one is probably about 7 or 8, I would guess. And then for the blue one, it looks like it's 20, right? So it looks like the mean of distribution 2, since again, it's that the blue one is 2 and the red one is 1, if you look at the key that's up there in the right corner. So it looks like the mean of 2 is greater. So the mean of distribution 2 is greater. And so I guess we're just putting our true statements over here. And if we go up, I think that's B, but let me check. I don't remember how I configured those exactly, but I think that's right. Yeah, mean of distribution 1 is less than mean of distribution 2. That's what it looks like, right? It looks like the mean of distribution 1 is 7 or 8. Looks like the mean of distribution 2 is about 20. So yeah, that's B. Looks like it's true. So look for the hump when you're looking for the mean, right? Top of the hump, that's where it is. All right, and then which one looks like it's more spread out? 2, the blue one, right? It's shorter, it's got the thicker tails. So distribution 2 is, I guess has would be a better word there. I was going to say is shorter, but has a shorter peak is a better phrase. So has a shorter peak and thicker tails, and I believe that would be E. And if I scroll back up, Yeah, standard deviation distribution 1 is less than that of 2. Looked like 2 was bigger, right? So looks like that's it. Okay, so that sort of thing you can figure out just by looking at the picture, right? The mean is easy to catch just from where the hump is, right? That's how you would figure that out. And then if you're looking for which one has a bigger standard deviation, generally it's the one that's shorter and has the thicker tails, right? Really, it's about the thicker tails because that means it's more spread out. But if that's happening, then the peak is forced to be shorter to preserve the area under the curve being 1. So you can also do it that way. I guess that's sort of a shortcut in a way. If you just go, well, the shorter peak would have to have the thicker tails, therefore the larger standard deviation. That will always work. So you could use that as a shortcut. All right, then common shapes. So that basically covers all of these specifically normal distribution related material. But the common shapes that you can have are symmetric ones, like a normal or like a uniform, right? Because that's just flat across. Otherwise, you can have ones that are skewed, so left skewed, right skewed. So basically the skewed ones, the only thing I think you have to worry about is remembering which is which. Because figuring out that you have one that's skewed isn't that bad, right? If it's not symmetric, if it's got one tail that's short and one tail that's long, that's skewed. But which is which? Which one's right skewed, which one's left skewed? The names go along with the long tail. So like here, in the sky blue one, you got the peak, and then you got the left tail. It doesn't really stretch out that far, right? Because the left tail only goes about over there. Then the right tail goes like way over there, right? So you got this long right tail. So long right tail, that means right skewed. So long right tail is right skewed. And then over here, let's see, the peak's about there. So left tail goes over that far, right tail goes way over there, right to about 50. So this one, long left tail, right? So long left tail is left skewed. So you just look at the tails as far as like how far they stretch horizontally. And if you have one that goes out a lot farther than the other, then you've got a skewed distribution, and the type of skewness goes with the long tail. That's the way that I've always made sure not to get that backwards. I just think name goes with the long tail, name goes with the long tail. But that is the way that it works. And none of the shapes have to be absolutely perfect, because like if you look at this green one, that's not a perfect bell, but if you were going to draw in a best fit curve, then that's what you're going to end up with, right? You're going to get something like that, and that's a bell. So it doesn't have to be a perfect shape, especially if you have a histogram, right? A histogram is made up of rectangles. It's probably going to look a little bit jagged. That's fine. There's nothing wrong with that. So to be considered bell-shaped or symmetric, it just has to be approximately bell-shaped or symmetric. It doesn't have to be perfect. Just like, and even the uniform, the red one, right? That's not perfectly flat across the top. That's all right. It's almost that, right? So it's, it's almost a perfect uniform shape. You would still call that symmetric. All right, next. This skewness thing just goes along with what was up above it. So right skewed, long right tail, left skewed, long left tail, right? That's the key right there. So those, that's the thing I think you really need to remember for skewness. It's just the type of skewness goes with the long tail. All right, there are some questions in the homework where you have these sorts of things where you have the frequency table and you can figure out the skewness. Although in the homework, it's usually, I think it's more like you have to pick the right one out of a lineup. Like, here are 4 frequency tables, pick the one with the left skewed distribution, that kind of thing. But I think if you can make one, you can pick one out. Because making one from scratch, I think requires a little bit more mental energy. So that's why I kind of thought maybe this was the way to go. But we're supposed to make one first for this frequency table on the left that's right skewed. So right skewed, you want to make a long right tail. So how do you make that? I would say that first just designate where you're going to put your peak and then kind of go from there. So I'm going to put the peak let's say, like, because I need to make a long right tail. So that would be as the values get larger, I need the long tail. So I'm going to put the peak like way back toward like 1 or 2. So I'm going to put it at 2. Let's say I make this like 55 for the frequency. And then I just have to make a little left tail. So let's say then this one's like 31 and then this is 8, right? So really quickly, as you go 2 to 1 to 0, it goes down, right? So if you were going to make a histogram, it would be like big bar, then bar that's significantly smaller, and then bar that's really little. I'm going over to the 0. And then I'm going to stretch it out going this way. So let's say maybe I've got like a 39, a 26, a 14. So I'm just gradually going to get smaller and smaller, like a 10, a 7, a 3, a couple of 1s, right? So there we've got our peak here. And then gradually, like if you just think about, like almost like if you could rotate the page so that you had the 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 on the bottom. And then you can sort of visualize like a bar of height 55, then 39, 26, 14, 10, 7, 3. They get smaller and smaller and smaller, but that's taken a while to get all the way down, right? Like that's stretched out pretty far horizontally. But then the left side, you get down real fast, right? So short left tail, long right tail. Because everything, like as far as where the tails begin, think of them as beginning at the 55, because that's your peak. So you only go a little bit over toward the left, right, with the lower value, so for the 1 and the 0. But then you go way out for the right tail. Right, so long right tail, short left tail, that's right skewed. So if you had to make one that was left skewed, you'd kind of do the opposite. Like maybe you put your peak at like 8 or 9, and then you have a long left tail stretching way out, and then you have a tiny little right tail. So, right, kind of the reverse of what we're doing now. Roughly symmetric. Okay, put the peak in the middle. There are 11 possible values. I'm going to put the 6th one, which is the 5. So I'm going to put some giant number up here. Let's say we got like an 86. And then I'm going to gradually get smaller in both directions. So let's say like maybe there's like a 63 here and like a 66 there, right? So not exact, but close, right? And then maybe something around 50, so like a 51 there. Maybe here, I don't know, 49. Then mid 30s, let's say, like 36 and 35. We'll keep those almost the same. Maybe mid-teens, like a 15 and a 12. And then something single digits, 3 and a 7, let's say. So then in both directions, you get smaller and smaller and smaller, and it's not a perfect match, right? Like 63 and 66 aren't the same number, but they're pretty close, right? 51 and 49 aren't the same number, but they're pretty close. And I did that on purpose where none of them actually match. But it's the same pattern going both ways, and there are just those slight variations between 63 and 66, and between 51 and 49, between 36 and 35, and so forth, right? So it doesn't have to be perfect, right? Roughly symmetric was what we were going for, and that's still pretty symmetric. You got your peak right in the middle, and gradually in both directions it goes down, then down, then down, then down, the farther away you get from that peak in the middle. So that's how you would pick them out too. Like if you saw one that kind of looked like this in number 4, you'd say, oh, that's roughly symmetric. If you saw one like a number 3, you go, well, the peak is at 2, so that right tail is really long and the left tail is short, so it's going to be right skewed. And I guess if you saw the opposite of something like in number 3, then that would be left skewed. All right, I think that covers the skewness with the frequency tables. There is actually a question, because I ran the homework twice and I got one of these each time, where it involved box plots. And I thought, like, this is a little out of chronological order because box plots are actually covered in 3G. But the way that you check for skewness, we can cover that without going too in depth about how you get the box plot. But basically the way that you get one is that you need to go through quartiles, and that's a big thing in the next section. But basically, you get your first and third quartiles, which are the 25th and 75th percentiles. That's how you get the box. So it's like you make line segments at those, and then the other 2 line segments that would make the box, you just sort of connect them together. And so like if you look at these down here, like this symmetric one, we can see that whole thing. The left and right sides of the box would be determined by the quartiles, by the 25th and 75th percentiles. The median is the line inside the box, and the whiskers extend to the extreme value, so like the max and min. So if you have a symmetric distribution, then you get the median right in the middle of the box, right? And you get your quartiles are about the same distance away from that, and then your whiskers are about the same length. So what you end up with is something that, you know, the left and right sides, maybe they're not exact mirror images, but they're not too far from it, right? And that's what we got there. But what happens with the skewed ones is basically that you get one side really stretched out and the other side looks compressed. And that's kind of like having one long tail and one short tail, with like with a histogram or with a frequency table. So with a right skewed distribution, basically you end up with the right side being really stretched out. So like the median, third quartile, and max, like those three are kind of stretched out. And then the left side compressed or close together. So the minimum, first quartile, and median. So there it is. One that's right skewed. So the median's that line inside the box. And then, right, so then like right there is the median. So like that, and then the third quartile, which symbolically you would do like that, like a Q3, and then the max. So notice how stretched out these are, right? Like there are big gaps in between those. But then if you go toward the left side, the first quartile, which we would write as Q sub 1, and then the minimum, which is that whisker all the way over on the left, those aren't as spaced out. And that's the idea. So then, like, what would be the left side, the minimum, first quartile, median, relatively speaking, at least, they're close together. But then the right side, which would be the median, third quartile, max, those are stretched out. And then for a left skewed distribution, you get the opposite, where then the left side is spread out and the right side is compressed. So if you look at that one, there's the left skewed. So again, like that line inside the box, making a mess. All right, the line inside the box, let's do that again. That's the median. And then right side of the box is the third quartile. Left side would be the first quartile. And then way over here on the left, you got your minimum. And then way up here on the right, the end of that whisker, you got your max. So with this one, the right side is more compressed, right? Even if you just look at like how close the median and the third quartile are versus the median and the first quartile, right? Like the median is over toward the right side of the box. So the right side of what would be called the 5-number summary, which is what these 5 numbers are collectively called, your median, quartiles, and extreme values. The right side of it, the 3 biggest values, are kind of, you know, bunched up together, at least relatively speaking. They're not like right on top of each other, but they're certainly closer than the left side, which would be the minimum, first quartile, and median. So for left skewed, you still get the idea of like the stretched out left side and the squeezed together compressed right side. So having a box plot that looks like this is like if you had a histogram with a long left tail and a short right tail. And then right skewed, that would be like having a histogram, like with having the median, third quartile, and max all spread out. That's like having a long right tail in a histogram. Same effect. All right, so that does show up in this section, which is why I wanted to go through that, even though it's only one problem. And it does feel like it's a little out of order to me, but I can see why it's here, because it is about the idea of skewness. So I can see why it's here, even though box plots aren't really until the next section. All right, then relative standing. Things like percentiles actually factor into that, but percentiles and quartiles, they usually get talked about like they're separate things, which is why I wrote it this way, even though quartiles are really just specific percentiles. But those will get covered later. What we're going to cover right now are z-scores or standard scores. You can talk about z-scores within one data set as well, but when we're talking about relative standing, that's when we want to compare values from different data sets and be like, well, which one is bigger relative to the data set that it comes from, or smaller relative to the data set that it comes from, or more extreme, right, in either direction relative to the data set that it comes from. We can do all that stuff. A z-score or standard score, sometimes they're called standard scores because the way that you compute them is by standardizing, which is what it's called when you divide by the mean, or subtract the mean and then divide by the standard deviation. That's what I was trying to say. And what a z-score would tell you is how many standard deviations above or below the mean your observation or your specified value would be. So I've got it written in notation with the population measures and then with the sample measures. So the population measures, that's this first one right here where it's the mu for the mean and the sigma for the standard deviation, or with the sample measures with the x bar for the mean and the s for the standard deviation, right? It looks like you do the same thing either way, right? You just subtract the mean, divide by the standard deviation, and that's true, right? Whether you're dealing with sample data or if you happen to have population measures, it's still just subtract the mean, divide by the standard deviation, and there you go. And so what do z-scores tell you? Well, they would tell you how many standard deviations away from the mean your observation is and what direction. Because if you're getting a positive z-score, then x, which is the observation or the specified value, that's bigger than the mean, right? Because the standard deviation is never negative. So in order to get a negative number, you'd have to have x being less than mu, but then if x was bigger than mu, you'd get a positive number. All right, so a z-score of 1, that would tell you that your value is 1 standard deviation above the mean. Right? So 1 is 1 standard deviation away, but because it's positive, it's above. Then -2, well, that's 2 away, but more specifically, it's 2 below, because the negative tells you it's below. And you don't have to just have integers. So like if you had a -0.6, that would be 6/10 of a standard deviation below the mean, right? Below because it's negative. All right, so mainly what we're going to be concerned with is comparing values from different distributions. In this example, I had to use because the new scoring system for the GRE I find very perplexing and arbitrary and strange. So before August 2011, the scoring system was like the SAT, where it was like low of 200, high of 800, which still feels a little arbitrary, but at least that's one that's been floating around for a while. Then it changed to where the worst possible score was 130 and the best possible score was 170. I have no idea why anyone would pick that and go, yeah, that's a thing that's easy to understand, but apparently someone did, and that's the way it works now. So the means and standard deviations, like these are readily, like publicly available. So these are easy to get, like the population mean standard deviation for the GRE scores before and after this unusual change of scoring system. But clearly you couldn't compare values directly. So let's say you had a couple of people who took the GRE, but one of them took it before the switch and one took it after. So what's better? 720 on the quantitative reasoning section in December 2010, or 160 on the quantitative reasoning section in November 2012. Clearly, you couldn't just compare the numbers directly because a 720 is impossible with the new system and a 160 is impossible with the old system, right? Like you have to sort of figure out what they are relative to that scoring system, right? Like the 720, like what's that relative to the 200 to 800 scoring system? And how the scores were distributed with that. And then the 160 relative to the 130 to 170 scoring system. All right, so we have the means and standard deviations for both before and after the switch. So we can figure the z-scores out. So the 720, oops, it would help if I turn the pen on. 720 in December of 2010. All right, so the z-score, so z would be, and I guess those are population measures, so I could write it as x minus mu over sigma. But if we sub in, then x is just your observation, which means that's just the value that you're you're interested in, I suppose. So 720 minus the mean for the old scoring, which would be 584, divided by the standard deviation, which is 151. So then that means what you're going to get is 136 over 151. And to two places, that's 0.90. I think that's what our homework asks for, is two places. And that's pretty conventional for z-scores. So we'll stick with it. All right, then we just have to get the z-score for the other one. So a 160 in November 2012. All right, so same idea. So z will be x minus mu over sigma. And so our observation here, the x is the 160, right? That's the value that we're concerned with. Minus the mean with the new scoring system, which is 153 in that second bullet point, and then divided by the standard deviation, which is 9. So it looks like what we're going to get is 7 over 9, which to two places is 0.78, right? You get 0.777777 repeating. So to two places, 0.78. Okay, so based on the z-scores, the 720 in December 2010 had a larger z-score, so that's the one that's better. So we'll say that the 720 in December of 2010 is better since the z-score is higher. Oh, there's one other thing I figured I should mention, because I'm sure some people are going to notice this and think that it's weird. Why? I'm just going to circle this in a different color. So this is just a fun fact now. If you don't want to see this part, you can just skip to the next page where I am in the video. But why is this mean so high? Because you think, like with the SAT, it's supposed to work out to where the mean is 500. Right? Like that's how it's supposed to work. And that's how this is supposed to work. But 584 is huge if you're supposed to get 500. Like, why is it so big? The reason that it's so big is mostly because of econ graduate programs, actually, economics graduate programs. Because there are some that in order to get in, you have to get a perfect score on the quantitative reasoning. So what'll happen is that people who are aiming for those programs, they'll get close, but they'll keep retaking the GRE. So they'll get like a 780 and a 760, right? And things like that. And then, you know, if they have to take it 4 times to get the 800, then they'll take it 4 times. But all 4 of their scores go in. So it's not like it's one score for one person. It's not like they average the 4 scores for that hypothetical graduate student. It's all of those go in there. And so that's kind of what happens. The people who take the GRE repeatedly tend to be people who are trying to get some really high value. And a lot of it's that. Like, it's people trying to get an 800 to get into, like, you know, the University of Chicago's econ department or something. And because of that, the quantitative scores are really distorted. I think now, if you get a perfect score, so like if it was in the old system, if you did get an 800, you end up in like the 93rd or 94th percentile, which sounds ridiculous, right? You would think if you got a perfect score, then you should be like up at the top, like the 100th percentile. But it's because so many people end up doing that, you end up with kind of distorted, weird looking percentiles for the quantitative reasoning. And that's also why the mean is so high. So I figured I should at least point that out, because I know some people are going to look at it and be like, there's no way that's right, that it's 584. It can't be that high. But yeah, it is. And there's a weird reason for it, but there is a reason for it. All right. So anyway, moving on. Okay. I picked Yellowknife because I wanted a place that's really cold. So that's kind of an obscure city to pick here, but that's why. That was the first one that popped into my head. I thought, where's a really cold place? So Yellowknife, and if you don't know where it is, it's in the Northwest Territories, which is one of the 3 Canadian territories that's above the provinces. So it's way up there. Apparently, you can get very nice views of the northern lights in Yellowknife. I've never tried it, but apparently you can. And this is real data too. So like I actually like pulled all of this and did the computations myself. Not for all Januaries, but I pulled a bunch of what they had and did it. So the mean is negative 12.7 degrees Fahrenheit with a standard deviation of 12.3. And in Phoenix, the mean temperature in January is 55.5 degrees Fahrenheit with a standard deviation of 5.3. Okay, two things are noticeable there, one of which is obvious without the numbers. Phoenix is warmer by a lot. Well, yeah, right? We don't need the numbers to know that. The other one that without the numbers would be kind of hard to figure out is look at these standard deviations. There's a lot more fluctuation in Yellowknife than there is in Phoenix, right? The data are much more spread out because the standard deviation is a lot bigger, right? It's almost 2.5 times the standard deviation for Phoenix. That will factor in here. So if we've got what we've got here, and notice that I kind of intentionally picked numbers where the difference is roughly the same from the mean. So let's say there's a day in January where it's negative 23 degrees Fahrenheit in Yellowknife and 44 degrees Fahrenheit in Phoenix. Both of those, I was aiming for, you know, like rough, like basically I just truncated and then subtracted 11, right? So it's cool, like in both, like it's cool or it's cold compared to what usually goes on in January. But which one of those is going to be lower relative to the January temperatures of that city? I mean, in absolute terms, it's Yellowknife, but it's always going to be Yellowknife, right? A hot day in Yellowknife in January is still going to be extremely cold in Phoenix, right? So we can't just compare them directly. So we're going to use the z-scores. All right. Well, then if we do that, so let's see if we have... Yellowknife. All right, so we're going to get our z-score. Then let's see, it was negative 23 for our observed temperature minus negative 12.7 for the mean, and then divided by 12.3. All right, so then 23 plus 12.7, right? Because minus and minus is a plus. So you end up with negative 10.3 over 12.3, which is about negative 0.84. All right, and then what about Phoenix? We get the z-score for a 44 degree day in Phoenix in January. So that'll be x minus mu over sigma again. And that's going to be 44 minus, let's see, 55.5 over 5.3, right? So just make sure you use the right mean standard deviation for Phoenix. And other than that, you're kind of doing the same thing. This will end up being 11.5 over 5.3, or negative 11.5 over 5.3, which is negative 2.17 if you round to two places. Okay, so how about our conclusion? And how about a different color? Let's say the lower relative to, I guess, January temperatures of that city. It's the 44 degrees in Phoenix, since the z-score is lower, right? We got negative 2.17 for Phoenix. We got negative 0.84 for Yellowknife. So lower z-score is going to be the lower relative temperature. So 44 degrees in Phoenix, since the z-score is lower. Okay, then that's one question, and then I wanted to have a second follow-up question where it was just which one is more extreme, where like one place is having a hot day and one's having a cold day. So, all right, with B, Yellowknife's having a hot day. Right, all that hot air coming in from the Arctic, I guess, because that's how that works. Um, but Yellowknife kind of having a hot day, right? 15 degrees Fahrenheit would be really warm in January there. And then 40 in Phoenix, a cold day. So which temperature is more extreme? Okay, more extreme is going to end up being just which one's farther away from the mean, and the direction doesn't matter, right? Because clearly these are in opposite directions, right? One of them would be really, really warm, like the January thaw of Yellowknife, and then one would be pretty cold. So let's see what happens. And I guess it wouldn't really be much of a thaw because it's still way below freezing, right? So you wouldn't really get any melting or anything. Um, but let's see what we're going to get for our z-score. So x minus mu over sigma. Just now our x is 15, right? So 15 minus the Yellowknife mean, which was negative 12.7. And then divided by the Yellowknife standard deviation, which is 12.3. So then z is going to be 27.7, because it'll be 15 plus 12.7 over 12.3, and you get 2.25. Okay. And then, another thing I should point out. I need to interject this at some point. Since I'm thinking about it now, this is a good time. If you get a z-score where you're more than 2 standard deviations away from the mean, that would be considered an unusual value in general. So this would be unusual, but yeah, I mean, we can look at that and see that right away. Like when usually it's below 0, right? When the mean is negative 12.7, but you have a day where it's 15, like that's out of the ordinary, right? So that's one where I think intuitively you can figure that out. I don't think you really need the numbers, but generally that's the way that it's thought of, is that anything where the z-score, I guess, would be bigger than 2 or less than negative 2 would be considered unusual. So let's see what we get for Phoenix. Maybe we'll get something unusual here too. So let's see. We probably will because the standard deviation is so small. But we'll get our z-score, so x minus mu over sigma again, so 40 is the Phoenix temperature we're interested in now, minus the Phoenix mean, which is 55.5, and then divided by the Phoenix standard deviation, which is 5.3. So the z-score here is going to be negative 15.5 over 5.3, which is negative 2.92. So I think at face value that Yellowknife one probably looks crazier, right? Just because the absolute difference between that and negative 12.7 is so big, right? I mean, that's a difference of almost 28 degrees, right? That's a lot, right? No question, that's a lot. And with Phoenix, the difference was only 15.5 degrees, but the difference in standard deviations is what's throwing this off. Right, the Phoenix standard deviation is much smaller, so because of that, right, like the temperatures are much more bunched together. So then a difference of 15.5 relatively ends up being bigger because negative 2.92 is farther away from 0 than 2.25. And that's kind of what you use to answer this. So we'll say that the z-score of the Phoenix temperature is farther from 0 So it's more standard deviations away from the mean. And I guess you could think of this in terms of absolute value if you wanted to. In a way, like you can say, well, negative 2.92, that's 2.92 standard deviations away, right? It's 2.92 below. But right now, for which one's more extreme, we're just trying to figure out how far away from zero are they. 2.92 is farther away than 2.25, right? So that's really what it comes down to. So more standard deviations away, more extreme, right? So that's kind of what we end up with. So more standard deviations away would be more extreme. So then, in other words, to actually answer the question directly, the Phoenix temperature is more extreme, right? And it's because the z-score is farther from zero. That may or may not come up. I know there are ones that come up where it's, which one of these is better, or there are ones that involve things like running, where then which one is better would be the one that was faster. So it would be the actually the lower z-score rather than the higher one. But the idea of comparing the two z-scores, I think those three examples got all three options in there, where you're looking for the one that's bigger, you're looking for one that's smaller, and then you're looking for the one that's farther from zero. I think that's really about all you can do with them. But they're great for comparing values from different data sets, right? Because usually you can't compare them directly. It's very rare that you would have two separate data sets with identical means and standard deviations when you could just say, oh, we can just look at them directly. We don't have to do anything else. That rarely happens. So being able to just standardize everything, compare the z-scores, that really helps when you want to compare values that come out of different distributions.